Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about example which is commonly found in physics, and here is a direct application of higher derivatives. Well, as you can see here, this is the position function s is equal to ft and is given by this equation, and this is just a polynomial of degree 3. So t here is the time measured in seconds and s is in meters. Well, if you have the position function s is equal to ft, and if you differentiate this function one time, the result is going to be ds dt, and this is just the instantaneous rate of change of displacement with respect to time, and we can call it simply as velocity at time t. So here is the result of the first derivative. Okay, so you differentiate this function one time. Now let's see that if you differentiate the result here, so if you differentiate the result here, it's going to look like this. And mathematically, it can also be denoted as d squared s and dt squared. And this is the notation which you have already seen in chapter 3. And it basically means the instantaneous rate of change of velocity with respect to time, or in simple word, we will call it as acceleration at time t. So here we have differentiated this function twice. So this is the second derivative. Now if you go on and differentiate the result here one more time, so here we have the result of this, which is going to be differentiated with respect to time. So that brings us to this third derivative. Okay, so here is going to be mathematically denoted as such, and basically it means the instantaneous rate of change of acceleration with respect to time, or it can be simply known as jerk at time t. So here is the function being differentiated thrice, and we will call it as the third derivative. Okay, right, if we get on with our example here, the question is asking you to find acceleration at time t, which means that you have to differentiate this function twice in order to get acceleration. And once you have obtained that, you can find the value of acceleration after 4 seconds by substituting this value into t. Okay, so let's do it right now. Here we have ds dt, which is going to be equal to differentiating the function t cubed minus 6t squared plus 9t, and this is going to be equal to 3t squared minus 12t plus 9. So that is the result of the first derivative. So we move on and differentiate the result here once again. So we have this result, and you differentiate that once again, you will get the second derivative of this function here. And so the result is going to be equal to 6t minus 12. So this is the answer that we are looking for. Acceleration at time t is equal to 6t minus 12, and therefore acceleration after 4 seconds is going to be equal to 6 times 4 minus 12, and this is just equal to 12, and the unit is going to be meter per second. Yeah, Right, now I'm just going to explain to you a little bit about the unit. I hope everybody understands why the unit is as such, but you know, let's not take this for granted. I'm just going to explain how do we get this unit, yeah? Well, let's start off with the unit for velocity. We know that velocity is defined as applying the limit of delta t approaches 0. Delta t is on this side, on the bottom, and on top here we have the change of position, delta s. And we know that the position here is described by meters. Okay, you can see that based on the example here, s is in meters, it is measured in meters, so the unit is in meters. So if you talk about the unit, well, the unit here is in meters, which can be simply labeled as m, so the unit is in meters. So, and the top part here is the unit time here is in seconds, which is s. And so if you talk about the velocity unit, it's going to be the unit is going to be equal to m over s. So we call that meter per second, and sometimes it is also denoted as such. This is common notation, or sometimes it is also given in terms of s, and here we have -1. Okay, so that's the unit for velocity. Now let's talk about acceleration. So when we talk about acceleration, this is just applying the idea of limit, where limit delta t approaches 0. On the bottom part here we have delta t, and on the top part here is we have the change of velocity. So delta v is the change of velocity. On the bottom part is the change with respect to time. Well, if you can see here, the unit for velocity is meter per second. So here the unit is meter per second, and the unit for time is again second. So therefore, if we talk about the unit of acceleration, it's going to be equal to meter per second. And this is the same thing as having meter per second, okay, times 1 over s. And this is just simply written as meter per second squared. Sometimes the notation is as such, okay, or it can also be in terms of this, okay. Right, so that's just on the unit, something additional, not exactly what is related to the example here, but well, there we go, we have done that part for question A. Now let's move on to question B. You are asked to graph the position, the velocity, and the acceleration functions for t between 0 and 5. Okay, so what we're going to do next is we're going to consider the position function first. And here we have the position function is given as s is equal to t cubed minus 6t squared plus 9t. And if you want, you can write down in terms of factors. So you can factor out t, so you will get t squared minus 6t plus 9. And I'm sure you can see that this part can be factored easily, and you will get the final answer is going to be t minus 3 times t minus 3. Okay, so if you multiply t with t, you get t squared, and then t with -3, you get -t3 plus here is also -3t, so the answer is going to be -60, and then -3 times -3, you will get +9, and this is just t minus 3, and you square it. Okay, now based on this position function here, I hope you can see easily that s is going to be equal to 0, when t is 0 or t is equal to 3. Yeah, so if you plug in the value of t0 or t3, the position function on here s is going to be equal to 0. So we've got some easy points to plot, and we can do that right now. So when t is 0, s is 0. When t is equal to 3, s is equal to 3. So here is the axis for time. Let me just label this properly. So here is time. Okay. Right, now let's move on to this part. Now maybe we can find some other interesting points, such as when t is equal to 1. So when t is equal to 1, s is going to be equal to 1 minus 3 squared, and it's going to be equal to 4. When t is 1, s is going to be equal to 4. Yeah. Next, when t is perhaps equals to 2, s is going to be 2 minus 3 squared, and this is going to be equal to 2. Right, next, if t is 4, when t is 4, s is going to be equal to 4. 4 minus 3 is 1, so s is going to be equal to 4. And finally, when t is equal to 5, s is going to be equal to 5. 5 minus 3 is 2 squared. So 5 times 4 is 20. So these are the values that you can easily plot as well. So let's do that. So when t is 1, s is going to be equal to 4. So 1, 2, 3, 4. So this is the point. And when t is 2, s is going to be equal to 2. This is the point here. Alright, so next, when t is 4, the result is going to be equal to 4. So it's somewhere here. And when t is 5, the result is going to be equal to 20. Okay, I'm just marking the position correctly. So this is 20, yeah. Okay, so here we go. And our job is to connect the dots with a smooth curve, which may look like this. Okay, so this is going to be a smooth curve. Something like this. Yeah. Well, I hope it looks all right to you. So now I'm just going to sketch it properly, to draw the line properly. Okay, so maybe something like this, yeah. Okay, I hope that looks all right to you. Okay, never mind. Let's just pretend that it is okay. All right, yeah. Okay. Right. Basically, this is how the graph is going to look like. Okay. And here I'm just going to label s is equal to t and t minus 3 squared. Oops. Hang on. Okay, so that's the first graph for position function. Now let's move on to velocity. All right, so for velocity, maybe I will just erase this part. Oh, never mind. Okay, so for velocity, what we have is we will have the following function. So for velocity, v is given as 3t squared minus 12t plus 9, yeah? So based on this, I'm just going to write this expression into factors. So I'm going to factor out 3, and here I will have t squared minus 4t plus 3. And I hope that you can see this one here can be factored easily, and it becomes 3t minus 3 and t minus 1. Okay. Okay, so based on that, I can clearly see that my velocity is going to be 0 when t is equal to 3 and t is equal to 1. So here I have got some easy points to plot. So when t is equal to 3, the value is going to be 0 velocity, and the same thing when t is equal to 1. Right, and perhaps other point of interest will be when t is 0. So when t is equal to 0, v is going to be equal to 3, negative 3, negative 1. Or clearly from here you can also obtain the value is going to be equal to 9. So v is going to be equal to 9. So when t is 0, v is going to be 9, which is somewhere here. Now, how about when t is equal to 2? When t is equal to 2, v is going to be 3, 2 minus 3, and 2 minus 1. So here we have 3, negative 1, and 1. So it is negative 3. So when t is 2, this is equal to negative 3. And perhaps maybe we can find, since we know that this is just a quadratic function, this is a quadratic function, and the value here is a positive value, we know that the graph is going to be smiling like this. So perhaps we can consider the last point, which is t is equal to 5. So when t is equal to 5, v is going to be 3, 5 minus 3 is 2, 5 minus 1 is 4. So 3 times 4 is 24. Okay, so this is going to be equal to 24. Right, so let's plot 24. So 24 is going to be somewhere here. Okay, now that is quite a hard job to try and get a good curve out of this, but let us give a try. Alright, so it's going to be looking like this. Alright, and just, trying to mark some of the points just to see how it looks like. Okay, let us try and connect the dots now. Well, I guess that looks alright. Okay, right. Just give me a moment to, do it properly. You really need a steady hand for this. I don't think it looks any better, but well, I hope you get the idea. Anyway, okay. Well, let's assume it looks okay. Let's just pretend it looks okay, right? Okay, so that's how the quadratic function looks like. So I'm just going to label this as v is equal to where's the function? Okay, 3 t minus 3 and t minus 1. Okay, so that's the velocity function. Now let's move on to acceleration. Okay, so for acceleration we have this function written as acceleration. For acceleration we have the result is 60 minus 12, and this is just a straight line, so it's going to look like this. So here is the slope is positive, so it's going upwards in this direction, and we know that the intercept is at point -12. Okay, so the intercept is at -12, which is somewhere here. And when t is equal to 0, so sorry, when t is equal to 0, when acceleration is 0, I'm sorry, so next is to find what's the value of t when a is 0. So when acceleration is 0, then 60 minus 12 is equal to 0. 60 is 12. T is going to be equal to 2. So we have another point, which is this one here. And we're just going to draw a straight line, and thankfully I have this fancy ruler which I can use it to get a straight line. This is cool. Okay, I just need this. Okay, this is not as easy as it looks. I thought it's going to be easy, but not really. Okay, yep, something like this. So I'm just going to draw a straight line. So that's the graph for acceleration. I'm just going to continue until t is equal to 5. Yeah, hang on. Okay, this is not as easy as it looks, but at least you get a straight line. That's the point. There you go. And I can continue until 5. Okay, so I guess that will do. So this is how the graph looks like, more or less. Okay. I'm just going to label this graph as a is equal to 60 minus 12. All right. Okay, so there we go. We have done question B. Now let's move on to the next question, the last question, which is when is the particle speeding up and when it is slowing down? So for this part here, what we can do is we can refer to the velocity. Sorry. We can refer to the velocity graph given here. Okay, now you can see that from between 0 to t, between point 0 to t, the velocity here, the point here is the value here, the value of velocity is going down. So that means at this time interval, it is slowing down. Okay, the particle is slowing down, and it will reach this point here when t is equal to 1. The particles are going to stop. Okay, and it is going to change direction because now the value here is a negative value. So here the velocity value is negative. So that means when you have a negative of something, that means the velocity is changing direction. But here is the point where it speeds up because the value here is actually gets larger and larger, although it is a negative sign. Yeah, so so the particle is speeding up at this point between t 1 and t equal to 2. So we can write down that the particle is speeding up when t is between 1 and 2. Now the particle is slowing down for when t is between 0 and 1. So it is slowing down. You can see the graph is moving downwards and it's ready to stop at this point here. So this is the process of slowing down. So at this point here, between 2 and 3, between time interval 2 and 3, the particle is slowing down because it's going to reach again the value of 0 here. So that means the particle is going to stop. So here is a process of slowing down. Alright, so here is a process of slowing down. So the particle is slowing down when t is between 0 and 1, and also when t is between 2 and 3. So that is slowing down, and then okay, when it reaches this position here, the particle stops, and after that the value of velocity increases. So that shows the particle is speeding up around this time interval, and the value here is positive. That means it is moving in the opposite direction as opposed to this one here. So here is the interval where the particle is speeding up. Okay, so speeding up when t is between 1 and 2 and t greater than 3. Okay, I think that's all for now. Thank you very much for watching.